So here is a Pa940s, a never 100 volt distribution amplifier. This thing is a brute. If you look here, there's 5 output transistors, TTC 5200s are they? 2SA 5200, something like that. And they're the top drivers. There's another 5 underneath the heatsink. Monster great big output transformer, power transformer. Oh, dearie me, my throat. And so yeah, I got lucky kind of turning this one on, because it started off really distorted and then cleared and then distorted again and then just seemed alright. So poking around for ages, I finally found, so somewhere in here, if I push on it, this is a very intermittent fault. It's a bugger to find. So let it go, it seems to go away, and that's with the feedback winding unplugged. If I plug it in, it manifests itself as a rather nasty, it'll do it, yeah, distortion, oscillation. Well, I'm having to keep, sometimes I can get it to stay like it, but it's very difficult. It doesn't seem to matter where I push on the bloody board. Ooh, stinking. It initially seems like it's somewhere here. I think, you know, there's a 24 volt regulator here, which pushing on it does it, but pushing around here doesn't seem to do it. Pushing it the back here, I can make it do it, but seems to be mostly here. Can't really pursue it even if I manage to get it to start doing it. As soon as I come in with the meter probe and try and touch anything, it just stops. So I'm going to have to pop the board, and I see that regulator is absolutely roasting. So yeah, going to have to pop the board out and see, because yeah, when it does it, it sounds terrible, and at the end of the day it means there's something wrong. So I'm going with either there's a duff regulator, nasty solder joint, or a cracked trace or something. But yeah, I mean, just pull the camera back. And this thing is, it weighs an absolute ton. That iron in there, that iron is significant. This output and power transformer are just like 2 solid lumps of boat anchor stuffed into an amplifier. So yeah, this looks like it could be fun. It's solid built. So someone had tried being in here before, because see if I can find one. It's typical, isn't it? So yeah, the screw heads are chewed up on several screws, and that's in the undo direction, not the do up. So yeah, someone's been in here. Something's not right. So yeah, I'm gonna have to pull it apart, see if I can figure out what is wrong with it. Another day, another amplifier on the bench, and another intermittent fault. Intermittent faults are the worst, because intermittent faults are intermittent by their very nature, and that means instead of having a constant fault that you know it's gone when it stops being a fault, intermittent faults, you can think you solved them, put everything back together, and you have to leave it running for hours and hours and hours and keep messing about, and all of a sudden it'll come back. They are absolute fuckers to deal with. So yeah, luckily enough, this looks like it should come out pretty easily. It appears there's some bridge rectifiers and stuff on a heatsink plate which bolts underneath. There's this main heatsink, everything's on push fit connectors, so should hopefully pop out of there with relative ease. Yeah, but that's the easy bit. The hard bit's going to be trying to figure out what the bloody hell's wrong with this. So yeah, I'm going to say it's a good chance that voltage regulators are buggers for breaking into oscillation and stuff. And you know, something's breaking into oscillation. I don't think it's the amp oscillating. I think it's more something on the board oscillating and injecting that into the amp. So I shall see. I shall see. This amp's quite interesting. All the other 100 volt line amps I've had that have used a push-pull type output transformer have had the output transformer in the collector circuit. So the centre tap-in has gone to V+, the plus 24, plus 35, whatever the rail voltage is. The emitters of the output transistors have gone to the negative rail, and the collectors going to the output transformers in opposing phase in a push-pull arrangement. So say the left set of transistors turns on and the collector voltage starts to fall. The set on the right hand side, which are turned off, the collector voltage will rise. Doesn't really matter, the only thing that happens is the voltage across the transistor that's turned off increases. However, this amplifier uses the emitters to drive the transformer. So what that means is the transformer center tapping is going to 0V. These are N-type transistors. The collectors of these are going straight to the V plus rail, the plus 35 volts or whatever it is on this amp. Let's have a look. Plus voltage on this amp is 40 volts. Look at that, 41 volts. And yeah, and the emitters are driving the output transformer in opposing phase, which means as one set of transistors starts to turn on and pulls that winding of the transformer slightly more positive, the opposing winding will actually drop below the 0V rail, which, as this is a single rail amp, would pose a problem, because if you had that transistor which has the emitter being pulled low, the base at 0V on it, as the emitter started to pull low, that transistor would just turn on. So there's a small drive transistor down here, not transistor, transformer, and the circuit is rather difficult to trace out because I don't know what the windings for that transformer are. It's just got 6 connections to the board on it. And I've not spent a great deal of time tracing it out, because after spotting that transformer I just thought I'd have a probe around. So let's say I put my meter on a lower scale. If I come to the base of the driver transistor, which receives its bias current through that transformer, if I push down on this cap, which is right next to where that transformer is, see that? It's losing all the voltage on this side, and it needs that to pull that base lower. It does it both sides. The other side it doesn't do it on. Yeah, it needs that to pull the base lower, because let me see if I can't draw this out a second, because I know it's one thing to explain, it's another thing to see. So if we look at my schematic here, which has clearly been drawn on my state-of-the-art CAD package. So here's the output transformer. 0V is this point here. Plus 40 volt rail. So these are the output transistors, these are the drivers. So as, let's say, this transistor is turning on to drive this one, we can pull this one up to somewhere near 40 volts, not 40 volts, 40 volts, that's the problem. So yeah, that could go, say, right up to nearly 40 volts, but because this winding is in opposition to this one, it has to have a reflection of whatever has appeared across this winding on it, but in the inverse. So if this was at plus 40, this would have to be at minus 40. While an NPN transistor, if you pull the base positive with respect to the emitter, that transistor starts to turn on. So if these transistors couldn't have their bases driven lower than the 0V rail, as soon as this transform started to drop below 0 volts, it would start turning these transistors on. So there's going to be some arrangement. This transformer, I've just drawn it as a real simple single-ended. So say this transformer is like this, and let's just say it's single-ended just to simplify things. As this transistor is driving this end of the coil, there'll be 2 equal opposing voltages this side. So if these ones are turning on, so let's say this one is at plus 40, this side will be at minus 40. So the emitter base junction on this transistor is still sinking at the same rate as this transformer, and so is this one. So it's going to be something like that, and whether it's a knackered winding or if there's a dodgy connection on the board here, but once this connection's broken, there's probably somewhere a resistor, maybe on here or something, going down to 0V rail. There's going to be loading resistors on this transformer, so there's going to be some kind of resistor, and it only needs the slightest bit of current path somewhere for these transistors to start being biased on. So as this transistor is trying to drive it, these are going to turn on and rob current from the transformer, and as this transistor is turning off, these won't turn on to take over. There's going to be lots of back EMF induced in the output transformer, which is going to sort of help give a sinusoid, but it's going to end up with the highly distorted sinusoid we saw, and lots of the oscillation and stuff, because it's going to start ringing around that at transition point where one transistor should take over from the other. So I've cracked out the 40-watt iron, and the first thing I'm going to do is just try soldering up these blobs on the board, because this is not a dual layer board, and this is soldered. I don't know why. Well, I know why they've soldered it to the underside. It's too big to fit on the top side, but basically it's, I don't know, how do you solder something that's soldered underneath where you can't reach the solder, but try and solder it above without a through plated dual layer board? That's interesting. If I tap this, see if I can crank the board. Oh, I still seem to have music play. Gives me a nice knock through the speakers when I do that as well. So what I really don't like with this amp is when you turn it off, you get a horrible speaker thud. You get, which suggests to me that transformer is being driven single-ended, and as the voltage to it collapses down, it generates a large voltage spike in one direction. We're a shit band, which causes a large momentary thump in the AC swing to the output transformer. So solder them up, see what happens. It's all I can do to start with, and if that doesn't solve the problem, I'm going to have to start doing some reverse engineering and maybe some modification. I shall see. Well, that seemed simple enough then. Yep, bending the fuck out of it now, and what's good is that is without the negative feedback plugged in. Shows, because the load is in the emitter circuit and the rest of the amp is already linearized with its circuit configuration, this actually runs quite well without negative feedback, and actually will have a very low output impedance. It won't be like that other amp I fixed, the 948 in the last video. Yeah, this is a completely different kind of circuit, and it sounds, yeah, to be honest, plugging the negative feedback in makes it just a bit quieter, gets rid of some hiss and stuff, but yeah, it that seemed to be the problem then, just that transformer. It's there you go, just a dodgy soldering job on that transformer. I'm going to pull this board out again, just see if I can check on the underside, but make sure I've got it as good as I can get it. But it's nice when you get the easy ones like that. Not sure what this thing's worth. It's a bit beaten up, to be honest. Let's turn that down before YouTube goes mental on. Yeah, plug that back in. Just some hiss. Hiss goes away. Well, she's a bit scratched up. So yeah, she's marked, but yeah, again, brand new, unused. I'm not sure. There's a QC mark on the board here. What does that say? The date of inspection? Christ. What do you make of that? Hang on. This is hard because I've still got the camera on the tripod. Well, not quite done yet actually. So I took the board off, and I just, was not happy at just looking underneath it, sort of what there was. So I've gone and put these basically just wires on. So if I move the tripod in, yeah, so you can see basically where the tracks are on the top of the board. I've just soldered some wires on. That now connects directly to that transformer. So yeah, I'm happy with that. It's definitely not going to crack and do that again. I'd still love to know the age of this thing. So I'm just doing some frequency testing. Well, just power testing more than anything else. So this is, you bear in mind, this is a transformer coupled amplifier. So, you know, going low frequency is tough on it. This is 50 Hertz. So you can see that that's distortion. That's actually the transformer core. Well, it could be the transformer core. It could be me. What's my AC I'm actually getting at the amplifier? where are my actual 40 volts? Yeah, somewhere near. Yeah, I'm going to say it's more core distortion, but what I thought was just more interesting, more than anything else, is how you've got to be real careful sometimes with your test equipment sometimes. So I'm just doing frequency. I thought I'll go lower in frequency, so I dropped to 100 hertz. No, it's not that one. Bear with me 1 second. It was the short. You never find the one you want when you want it, can you? So yeah, this one. So I dropped to 100 hertz. And I'm looking, I'm thinking, I'm look at that. I'm thinking, why am I so asymmetrical on my waveform? Look, I'm thinking, how nasty is that? Why is it? There's clipping, but what's going on? And it's actually because I'm going through an audio transformer. I'm driving the signal from the phone off hard. If I actually turn the phone down, there you go, symmetrical clipping. So I was actually, the signal coming in was distorted, but that's a 100 hertz. That's 44 volts RMS into a 16 ohm load. So let me turn that down a second. So you know, this isn't going to be an absolute all voltages and loads, but when I was just testing this a minute ago, 34 volts coming out the amplifier was 31.8 on the 4 ohm tapping, so that was actually stepping down slightly. 72 volts on the 70 volt and 105 volts on the 100 volt setting. So if you do the math, so the 4 ohm setting, if they will say 32 volts, we'll round it up, and I'm running a 16 ohm load here. So 32 volts, it's 16 ohm. If you want the amp to see that 16 ohm load as a 4 ohm load, and we can say that it can drive 32 volts happily out of the 4 ohm load, then it would need to be 64 volts to be seen, 16 ohm to be seen as 4 ohm. You double the voltage, you quadruple the power. However, if you then quadruple the load impedance, the amplifier sees it back to the original impedance again. It's quite a common mistake on valve amps. People think that the 8 ohm tapping will have double the output voltage on it than the 4 ohm tap, and it won't. It will have 1.414 times the output voltage on it, because then the 8 ohm load will still be seen as the same impedance as the 4 ohm. So I'm going to wire this 16 ohm load up to the 70 volt output, and then I'm going to see how much power I can draw out of this, because it's essentially the amp's going to see it slightly less than a 4 ohm load. I'll do the maths and work out what it actually sees it as. So doing the maths, 16 ohm on the 70 volt tapping relative to the 4 ohm tapping, if we go using the figures I originally measured, actually will come out at about 3.3 ohms or something. However, because the output transformer, the voltage coming out of it on 4 ohms was actually lower than what was coming out the amp, if you go by those figures again, the amp will just about be seeing somewhere very close to as if it was driving 4 ohms directly with a 16 ohm load connected to the 70 volt output on the transformer. So we'll do the brutal test. Let's give it 100 hertz and see what we can pull out of it. That's clipping, let's wheel back from that. Too close. I just want to come down a touch in volume on my, about there. So that's saying 70 volts RMS. See what my meter says. My meter says 63 volts on the 70 ohm, 28 on the 4 ohm. Yeah, so turn that down because I'm cooking my, what did I say? 60, was it 63? No, hang on. What was it? Let's go back a bit. Let's wind it up again. What I'm really bothered about is what is actually coming out of, that's clipping, let's wind it back. Yeah, 63. So what is 63 volts into a 16 ohm load? So 63 times 63 over 16. So that's 250 watts. So 250 watts at 100 hertz. Now let's see how much of that was down to transformer core saturation. Let's go up to 1 kilohertz and see the difference, see how high. I'm going to say you should be able to push it a fair bit higher on output power. Let's I'm not getting a high enough signal out of my phone to drive it into clipping. See if I can get a higher output signal. No, I'm just not getting it. I'm not getting enough output to drive it into clipping. Well, that's a shame. Let me see if I can just correct that a moment. There we go. Just change the tapping on the output transformer, well, the input transformer I'm using. So let's up the power. About there then, that is on the limit. So yeah, interestingly enough, not really a great deal more. So yeah. So yeah, I appear to be getting less at 1 kilohertz, which is just odd, to say the least. No, I'm getting exactly the same, 63 volts. It's just showing as a lower amount on the scope. So yeah, 250 watts on the 70 volt tapping. Well, I'll tell you, there's only one thing to do, isn't there? Is put it on 100 volt tapping, see what happens. So if we go by the turns ratio of about 3.0 something, basically 16 ohm on the 100 volt tapping is seen as 1.7 ohms. Now that sounds pretty drastic, but just bearing in mind there are 10 output transistors on this amp, and basically it's essentially, because it's 40 volt rails being reflected through the output transformer, it's basically a plus or minus 40 volt supply in essence. So yeah, 5 pairs of output transformers on just a mere plus minus 40 volts, 2 ohm load essentially, they should take it. It's just what will the transformer do? So we'll be brief here because my dummy load ain't going to take it long either. Let's see what we get, shall we? There, less, hardly anything. Transformer's just distorting. Yeah, nothing. Protection circuitry's kicking in then and just, yeah, stopping the amp from frying. I only just noticed, I keep hearing this little click sound and I think, what is that? And I'm like, I've only just realised it's the cooling fans for the amp coming in. So let's bake it for a little while. Let's, yeah, look, get far more out of it on the actual 70 volt tapping. See if we can get it up to a nice steady 50 volts RMS output. Don't know if you can see that. Well, 50 volts RMS into a 16 ohm load. What did I, 50 times 50 over 16. 156 watts. That's 156 watts. I've got some more resistors coming for the dummy load, so although it get red hot, like for instance in this setting they'd then only be dissipating like 35 watts each, so it presently is being asked to dissipate like 75 watts each, and they're hot. But yeah, she's starting to get hot. The heatsink is starting to warm up nicely. This is yeah, the joy of amp testing is power transformers protesting with quite a growl. You can hear it's loaded up as well. But yeah. So yeah, that's it. And just I'm just going to bake this for a little while and see what happens. So yeah, now a proper goodbye. So yeah, thanks for watching.